We've talked so far only about reactions that occur at the carbonyl group of our carboxylate. And now, as we did with chapter 17 and 18, we're going to switch our attention to reactions that occur in the position alpha to the carbonyl group. And there are three, all named after people whose name begin with H, which I refer to as the Triple-H reactions. We have the Hell-Vollhard-Zelinsky reaction, which is not named for the Vollhard from our textbooks, since there's no T at the end of the name. We have the Hoffman Rearrangement, and we have the Hunsdiecker reaction. These three reactions share in common that they involve reaction and the alpha position with a halogen, usually bromine, but it could be chlorine. And they also share, like Triple-H of World Wrestling Entertainment fame, that they will kick your ass if you're not very good at writing mechanisms. The Hell-Vollhard-Zelinsky reaction is analogous to alpha bromination of an aldehyde or ketone. The transformation is to brominate alpha to a carboxylic acid. So the net transformation is to take a carboxylic acid and by reacting this with bromine and catalytic PBr3, in position adjacent to the carboxylic acid. And that's a particularly useful reaction because now with a bromine leaving group here, it's possible to react this with ammonia and generate amino acids, alpha amino acids, in this case, phenylalanine, which is one of the 20 essential amino acids. And you'll notice that they exist as a Spitter ion. In solution, because the carboxylic acid proton has a pKa of about 5, where the ammonium group has a pKa of only about 9. Actually, because of the adjacent electron withdrawing nitrogen, carboxylic acid functional groups on alpha amino acids typically have pKa's closer to 2-ish. So much more acidic, that hydrogen comes off first before this hydrogen. So alpha bromination of carboxylic acid by the Hell-Vollhard-Zelinsky reaction can be a useful entry into amino acids. Racemic amino acids, right, because there's no stereochemical control, but nevertheless, being racemic amino acids are useful. The Hoffman rearrangement, the net transformation is to convert an amide to an amide with one fewer carbon. So if we have this primary amide, 3-methylbutanamide, treated this bromine and sodium or potassium hydroxide in an aqueous system. one amino, two methyl protein. Depending on whether you're using PAC or common names. The carbon that's lost, this one, and it's lost as CO2 gas. The Hunsdiecker reaction takes a carboxylic acid, to a halogenation, again with one fewer carbon. So the net transformation in the Hunsdiecker reaction is to take the carboxylic acid and generate bromide. And reagents for this are silver 1, usually as silver nitrate because it's one of the few silver salts that's actually soluble, and a source of base, or silver carbonate solid, which is not soluble but small amounts can go in, and then bromine. This is a free radical chain pathway. And again, liberates CO2. All of these involve bromination in a position alpha to carboxylic acid function. In the case of the Hell-Vollhard-Zelinsky reaction or HBC reaction, it's at carbon. In the case of the Hoffman rearrangement, the position that's being brominated is actually the nitrogen, which is still alpha to the carbonyl group, but it's bromination on nitrogen rather than bromination on carbon. And in the case of the Hunsdiecker reaction, it's actually bromination at the oxygen of the carboxylic acid to make a hypobromite. Where you have a bromine oxygen bond, as you would have in hypobromous acid. So they have in common being named after someone whose name begins with H, involving bromination in position alpha to a carbonyl group. But that's not all they have in common. And they're brominating on a different atom, carbon versus nitrogen versus oxygen. One of them is a free radical mechanism. This one actually involves a rearrangement, an alkyl shift. And the Hell-Vollhard-Zelinsky reaction is a multi-step pathway that begins with converting the carboxylic acid to the corresponding acyl bromide, and then tautomerization to the enol before the bromination occurs. Since this is under mildly acidic conditions, EBR3 is significantly acidic. So those are the three reactions, and what we want to do is take each one of those in turn and look at the mechanism for the